Hello everyone, welcome to lecture 4 of week 3. So in this week we have been discussing about word vectors and we have discussed the main frameworks of word2vec and glove already. Now in this lecture I will discuss about some other extensions that are very popular for word vectors. Specifically we will see various things. For example, how do we go for phrase embeddings, that is beyond the words. If we want to go for phrases, how do we embed those? We will look at using subwords for representation. So we have talked about subwords briefly, but can we also use them for getting better representation for words that may not be part of your vocabulary, and that's where the popular method of FastText will be discussed. And we will see how to go beyond just words. So can we go sentence and document label representation? So we'll discuss briefly the idea behind doc2vec, and we will see other extensions like how do we go for hierarchical representation, network representation, knowledge graph representation. This will be discussed in very brief. So let's begin with just mentioning about the glove vectors that is available publicly. So we talked about glove vectors in detail in the last lecture. So you can go to this particular link from Stanford NLP for glove, and so they have glove vectors for 300 dimensions, and also from Twitter word vectors for 200 dimensions made available. And you can see they are of different sizes depending on the vocabulary, different vocabulary that is being used, and different data source that is being used for creating this word vectors. But they are all available for download. So this is typically one of the best vectors that I use, glove 840 billion. But if you want to use a smaller size, you can also go for glove 42 billion. So you can download these and play and these for various applications. So now let us talk about how do we learn the phrase embeddings. So what do we mean by phrase embeddings? See, till now we have understood that in a corpus, if I have a word appearing, I can learn a representation for that, right? If it is part of my vocabulary that I have to fix a priori. But what about some collocations, some words that always occur together, like New York Times? Maybe in my data I have a lot of occurrences of New York Times, and I want to learn a single representation for this, right? So can I treat this as an individual word? Now this is not very difficult if you think about it. In the data, wherever New York Times occurs, I can just call it a single token, right? Maybe I can give some way of calling it a single token, like I am removing the spaces here and saying, okay, this is a single token. So wherever this occurs, treat it as a single token, and then I can learn representation for this single token like I am doing for every other token, right? So that is possible. But my question, the big question is, how do we know which of these multi-word phrases do I have to treat as individual tokens, right? So this will be replaced by some unique tokens, and by a diagram like this will remain as it is. I will still learn representation for this and it separately, while I will have a single representation for this. So the question is, how do you identify such candidate words? So idea is very simple. It's very similar to distributional semantics. So we need to find out which of such pairs they occur very frequently. So, and for that you can use a measure inspired by, say, point-wise mutual information. So what you will do, let's say we talk about bigrams, right? So I have two tokens wi and wj, and they are occurring together. So I'll count how often they occur together, like they occur together, divide by what is the individual occurrence multiplication, right? So if they are occurring a lot together, this would be a high quantity, right? And that's why I typically use this particular measure. You can compare it with something like a PMI measure, PMI which log of probability of word I, word j occurring together divided by probability of wi, probability of wj. That is, if they were independent, what would have been their probability? They were independent events. This is if they were associated. So it looks very, very similar. Like probability we finally compute as count of Wi, Wj divided by the number of documents and so on. Right. So it's very similar to PMI measure. There is no log, of course, because that's just a scoring way. And there is a minus delta. This just helps me account for very rare words. Right. What will happen if some words are very, very rare? Maybe their individual count is low, and they have occurred together maybe by chance. They are anyway very low. So this would, the quantity will become very, very large. So that's why we discount by minus delta, so that some rare word co-occurrences will not matter, and I will not just start calling some rare words as single tokens, right. So this is how it helps. So I use this minus delta as a discounting factor, right. And this was used to find out which bigrams I would call as single tokens. And now you can repeat this, right. So for example, in the first iteration you found New York should be a single token because of this is score above a threshold, right. Now again you will use New York and Times as two different words and see if their score is coming out above a threshold also. If so, you will call now New York Times as a single token, right, and learn only one representation for New York Times. So this was the method that was used in the original Mikolov's paper to find out which candidate phrases should be treated as individual tokens, and learned a single representation for that. Now let's talk about other kind of static embeddings. I am calling it static embedding because we will learn about some more dynamic or contextual embeddings in later lectures, right. So we'll talk about some contextual embeddings like embedding learns from language model, and even BERT kind of models will give a contextual embedding. So we'll talk about that in later lectures. Right now we are only talking about static embeddings. So FastText was another very, very popular method. Okay. So it handles one very important limitation of word to vec and glove kind of methods. What is that? So if you remember what we were doing, so from our data we are fixing our vocabulary, right. So vocabulary is always fixed. So vocabulary may be, even if it is a million, it's fixed vocabulary, right. So now you will learn the word vectors for all the words in the vocabulary. Now what it limits us to is, what if I create a new word, I have a new word in my data that is not part of my vocabulary, W that is not part of my vocabulary. So we call them out of vocabulary tokens. So what will I do for that? So typically the way they were handled was, you learn separate representation for something called unknown token, and just any out of vocabulary word you give it the unknown token embedding. This can also be some random embedding that is given to any such out of vocabulary word. Okay. So now how do we account for these out of vocabulary words? Now this is, if you remember, this was our motivation for introducing subword, right, in the tokenization part, byte pair encoding. So idea that FastText brought in was, can we learn the representation for these words by making use of the subword or their individual their spellings, like to say to use their spellings, what are the characters that are involved in these words. And this was from Facebook's AI Research Lab, now known as Meta, and this was very popularly used for word embeddings and also doing classification and other such tasks. Okay. And you can go to this particular website and get these word vectors. So let's discuss a bit on how this FastText method actually works and how it is different from the previous methods we talked about. So the objective function is very similar, actually it's the same as the one that we have seen in the case of negative sampling. Okay. So what is happening? Suppose I am at a position T, my word is at position T, and context position is C. Okay. And I am using this binary logistic loss, right. So this is 1 plus e to the power minus score of this position T word and the context word, right. And I have some negative samples. I have taken some n negative samples. So n is one of the negative sample in this, and I use 1 plus e to the power s delta T n, right. So n is a negative sample. So you remember this particular objective function. This is the log likelihood. So I want to so this is the particular function that we have anyway discussed in the previous lecture. It's very similar. Now what is the new thing that we are doing here? So the point is that I am not using the internal structure of the word. Here WT and WC are just the tokens. I don't care about the internal structure. Now what FastText does, it says why don't I use the internal structure to make it even much more stronger. So let's say you take the word eating, right? So what is the internal structure? Let's say what are the character 3 grams. So you have starting and EA, eat, ATI, TIN, ING, NG, end of token, right? So and this here, this eat may help in making it similar to say eaten, right? You may have another word like eaten, where also you will get a character trigram eat, right? And so on. So between these two words you will have this character n-gram common, right? And this can be helpful. Similarly, eating and playing, you will have ing common, right? So ing is a particular form that gives me an association between eating and playing, right? So can I use this internal structure using character n-grams? That was the idea of FastText. So like in eating, I can enumerate all the n-grams. So they started from character 3 grams to character 6 grams. So eating in 3 gram, you will have this that we saw. 4 grams, you will have eat, ET, and so on. 5 grams and 6 grams. Right. And we can also include the word itself, because in this case, eating itself has 6 characters, right? And if you use the starting and end of the word, it will have 8 characters. So this will not be part of one of these, right? 3 to 6 character n-grams. So we can also include the word itself. Now this is the entire set that is there in the word eating, right? All these character 3 to 6 grams and also the word itself. Now how do I use that? So what I will do, so let's go back to our formulation, right? Now my question is, how do I write this score between word T and word C, right? So here T is my say at position T the target word and C is the context word, and similar, this is the negative sample. So what I will do, so let's say I have a dictionary of all possible n-grams, right? So let's say I have all possible n-grams and I have created a dictionary. So these are my 3, 4, 5, 6 n-grams and the word themselves. Now given a word W, and let us denote so GW as a subset of this entire n-grams of all the 3 to 6 n-grams of word W that I can have. So all the set of n-grams that are appearing in W, right? So GW is all the n-grams of W, the one that we saw for eating. Right? Now we will have a vector representation to each of these n-grams. So I'll have a representation for eat, I'll have a representation for EA, I'll have a representation for NG at the end, right? I'll have a representation for each of these. And the simple heuristic would be, I'll represent the word eating by summing over the vector representation for all its n-grams, right? So I have all these n-grams, I'll get the representations for these or initialize the representation for these, add that, and that will give me the representation for the word eating, right? So this is how I will say. So for all words in my n-gram, I'll get the vector and multiply with the vector for the context word, right? And this is my scoring function, right? And this is how it is using the internal structure of the word. Now this I will use even for the negative sample. So this is the only change. So I mean, this is very similar to the negative sampling method that we saw, except that now I am using all the n-gram of a word to denote its vector, right? And this is what I will be learned. So through learning mechanism, I will learn the representation for all of these n-grams. Now one practical question can be that the number of n-grams that I get can be huge. Yes. So they use certain tricks for avoiding this, that you have to limit the number of n-grams. So what you can do, you can apply some hashing to bound the memory requirements. So instead of learning and embedding for each unique n-gram, So we will only learn total B embeddings. And B is my bucket size. In this case, they used a bucket size of 2 million. That means there are 2 million is the upper bound on the number of n-grams that you can have. So what you will do, so you from your unique dictionary of n-grams, you will have a hash dictionary of one of these B embeddings. So you will lose some information, but I mean there are 2 million possible n-grams that you can make use of. So not much. So each n-gram will be mapped through this hashing function to some bucket index, right? And that's what you will finally use, right? And you will learn embedding for each of these B buckets, right? So this was certain compromise that was done to ensure that you are able to fit things in memory and it does not just blow up because of the number of n-grams you are considering. Okay, and that was all. I mean, once you learn the embeddings, and there were many nice things that they could see. For example, connect versus interlink. So you can see which n-grams of connect and interlink are actually similar. So here you are seeing a representation where all the character n-grams of connect are denoted and all the n-grams of interlink are denoted, right. So and of course you can see there is a high similarity with link, right, and link and connect without a T, so they get a very high similarity. So you also get some sort of illustration, some sort of explanation on why two words are similar to each other. So you can see in terms of the n-grams that how they are, which subwords have high similarity. So here red denote positive cosine and blue are the negative cosine. Yes, and this word was out of vocabulary token in this case. So you can see in this particular paper they have many other examples on how different words can be compared by this method, right. And actually this FastText is available for many languages, not just for English, and we will talk more about this multilingual cross-lingual representation in the next lecture. So now we talked about FastText, that was again giving you a method for word representation by using the internal structure of the word. So we took all its character n-grams and added their representation to get the word representation. So that means at runtime, whenever you get a new word, what you will do? So simply you will average the vector representation for all its character n-grams, right? And that you have anyway learned. So any out of vocabulary words does not matter. You just average the embeddings of all its n-grams, right? Which are supposed to be present in the vocabulary. If they are not there, doesn't matter. I will use whatever is present in my vocabulary, right? And to get the representation. And this showed quite promising result. Now, but we can also go beyond words, like how do you represent sentences and documents. So there are many works for that. So we'll talk about one word that became very popular, that was again by Mikolov on distributed representation for sentence and documents. And idea was a very simple extension to the word-to-vec idea, right? And why this method is interesting, because otherwise what's happening, suppose you are given a sentence and you have to give a representation, like you have to represent a sentence, and this is very important, as we will see, I mean in the next week and so on, because if you have to do any task on the sentence level like classification, you would want a single representation for the sentence. Now if you just have a word representation at your disposal, how can you represent the sentence? One default way can be, you can take an average or sum of all the embeddings of the words. So the default way for representing larger units such as sentence was simply to use mean embeddings. You take embeddings for all the words, take an average. That will give you the sentence representation. And some papers also try to use some interesting way of taking the average, like you can take a weighted average, and weights can be TF-IDF weights. So some words that have a high term frequency, inverse document frequency, you can give them higher weight. The words that have a lower TF-IDF, that you can give them lower weight. Like the stop words need not feature so much and so on, right. But can we also learn a sentence representation by the same method? So that's where this doc2vec idea came in. So let's say you can compare the two scenarios. So you have this, let's say this is your unit, entire paragraph, the cat set, right. So the cat set on, right. So what you would do, you will get the embeddings for the cat set, and you will maybe concatenate them in CBOW, and or average them, and then you will classify and you will learn to predict the other word on, right. That was the idea of word to vec. In this case, what they said, fine, because I have to get a paragraph representation, what I can do, I can introduce a new vector for the paragraph, and this can also work for larger units like other units like sentence and document. So you initialize a representation for the paragraph that you want to learn, and the way you will learn it, that fine, given this paragraph ID and the other words, you predict the word that you are doing. So setting remains same, except that you have a new vector that you are adding to your input, the paragraph ID, right. You can of course take it to the other side also, you can predict the paragraph ID. So that's just another way of doing this, but that is the idea. You can just have a new vector for the paragraph ID, and you learn that in this process, because you will have multiple windows in the same paragraph. So using all that, you will predict the words, and in that process you will learn this paragraph vector. So this was one nice way of learning representation for larger units. Now coming to some other kind of extensions. So for example, in language, one interesting thing is hierarchy. So if you have seen WordNet, so in WordNet what happens, so different concepts are actually present in a hierarchical manner. So you have entity, now entity can have physical entity, abstraction, and then some words will finally, some actually, so these are some abstract things, and then some real entities would come later in this hierarchy, like New York, brain, influenza. So these are coming here. So there is an inherent hierarchy. So especially if you want to learn about hypernyms, hyponyms, it was not very clear how word vectors will denote this hierarchy, right. I mean, you can find out similarity between words, but how do you denote hierarchy? And that is where this very nice paper from Nikhil and Kaila, this came in. So in 2017, Europe, I think. So where what they proposed, they said you can use point care embeddings. So this actually assumes a point care ball and goes in a different goes, rather than going from Euclidean geometry, it goes for Riemannian manifold, and in that it tries to represent this hierarchy, right. So this was a nice work for hierarchical representation, and later on many works have also used it for denoting the hypernyms, hyponyms, and other kind of hierarchy in the language and other domains. So you may have a look on this point care embedding. So this is available, these vectors are also available for download. Now coming to a different kind of setting where this word to vec idea influenced is on graphs, like especially like how do you, if you are given a graph, so in a graph you will have nodes and edges. So can you get the node representation? Like how do you get a node representation, right? And this is very important for tasks that involve graphs, that if you want to do machine learning with graphs, you want to get some representation for the graph. And if you can get representation for the nodes, that would be very, very helpful. So idea was that you learn to represent this node in the dimensional vector, like we were getting the word vectors. And the word vectors idea actually influenced this field a lot. So initial methods were inspired totally by word vectors. Okay. So what you will do, for example, let's say I have two nodes u and v in my graph. I want to encode them in this embedding space, right. So very similar to our word embedding space. So let's say I encode u to get this gu and encode v to get this gv vector. Now what should be the criteria on which we have to encode? So the criteria can be very similar to like we are doing this glove and word to vec. So I'll say, okay, the embedding similarity between these two nodes should resemble something like similarity of these nodes in the original network. So there would be various ways in which I can denote similarity of nodes in the original network, and they should resemble the similarity of the embeddings, right. That was the idea, and this idea actually gave rise to many methods like deep walk and node to vec and so on. So for example, one way in which you can denote how similar these two are can be, okay, what is the probability that u and v will co-occur on a random walk on the graph? What's a random walk? I mean, suppose this is your graph. So you start from a point, let's say I start from here, and it has certain neighbors. So this has 3, 1 and 5, you can select a neighbor at random. That's why it's called a random walk. Let's say I select 5, right? Then again I select a neighbor at random, so it has neighbors like 6, 7 and 8, again the previous node, but let's say I select 8. So my walk is going like this, and then this, right? And if you think about this walk, it's like a sentence that you are creating, right? Sentence with various nodes. So you have this node, this node, this node, this node. So you can think of it like words in the sentence, right? So this random sequence of points that you have visited is like a random walk. So now you can construct this sequence of nodes, and you can use that in the same way that you are using the sentences or the windows in my word2vec model, right? So that's like you are using the W1 to W2, W3. Similarly, you can use the node 1, node 5, node 7, and you can say, okay, in this random walk, this should I predict another node given the other node embeddings, and so on. So one can use multiple ways to learn embeddings, right? And they had and this the loss function looks very similar to what we were doing in the case of word vectors. So right, it's very similar loss. So this is summing over all words by vocabulary. So GU transpose GN and GU transpose GV, the actual two words that was seen in the random walk, right? U and V co-occurring on the random walk, and you have used this loss function to optimize the embeddings. So this was just a direct extension of word vectors for learning embeddings on the networks. Now another thing that becomes very important from the NLP perspective is the knowledge graphs, right? So there are various knowledge graphs that encode information about various entities in the world, like Freebase, Wikidata, DBpedia, Yago, NEL. They are very much publicly available and very popular knowledge graphs, and they are very massive. I mean, they have millions of nodes and connections, but they are also incomplete because typically people provide information in them, and they may have some information still missing. And that's where a very important task, interesting task becomes that if you are given a massive knowledge graph, you cannot enumerate all the facts, but can you predict some plausible but missing links from that, right? Missing link prediction, can I do that? Like let's take an example. So this is what I mean by a knowledge graph. So you can say, for example, there are, so this is fantasy is a genre, and this is like J.R.R. Tolkien. So this is genre is fantasy, right? And there are various relations like influence. Stephen King influenced J.K. Rowling, and Stephen King genre is science fiction. What is missing is this one. So science fiction genre for J.K. Rowling, that is missing, and you want to predict that. This is the node J.K. Rowling, and you want to predict this missing genre, science fiction. So a knowledge graph will have all these head, relation, and tails, right? So you can say this is like, if I take this particular relation, this is the head, this is the relation, and this is the tail, right? Head, tail, and relation. That's what is a triplet in a knowledge graph. I want to predict some modes, some tails, and so on, right? So if I am giving J.K. Rowling and genre, the relation, what is the tail? So I want to predict science fiction. Now we can use the embedding idea, because if you remember, one good thing about embeddings was that they were I could simply use, so if H and T are two words, so the difference between the embedding was giving me some idea about the relation, right? So we found that uncle and aunt have, the difference is very similar as king and queen, right? So they were predicting some sort of relation just by the difference. So some very early methods use this idea, like TransE use this idea that, okay, suppose I have this triplet HRT. So I mean, that means the relation R between H and T. So let's say I put everything under some k-dimensional embedding, HR and T, embedding vectors. So as per this intuition, what should happen? So H plus R should be very similar to T, right? If there is a link between them, otherwise it should not be similar, right? So what they can do, so they can simply denote this particular scoring function. So if they have H, r and t after you have learned all the embeddings, and h plus r should be very close to t, and this is the scoring function. So if this magnitude, if they are very close, this will be close to 0, and that's what will be function. But if it is not too close, h plus r is not close to t, this value will be high, and I have a high negative score, right? So I want, this is a negation, so I always wanted low negative score, right, to be able to score the entity highly. So the first question that came is that how do you learn the embeddings, right, in this, by using this logic. And once you have learned the embedding, this can be a scoring function to predict between any h and t, right, is there a relation r or not. So they used a very nice intuitive idea. So what would you do? So you will take a knowledge graph, actual knowledge graph, where you have some positive triplets, say HRT. HRT is there in the graph, and you will also have some negative sample, so something that is not a corrupted triplet. So H prime R T prime for the same relation. H R T is there, and H prime R T prime is a negative sample. And I know the distance. So I know the distance between H plus R and T, and distance between H prime plus R and T prime. And I know this is the positive distance should be less than that of the negative triplet, right. So now how do I use this intuition to define a loss function? So I have defined a distance between positive triplet and negative triplet, and the one for positive triplet should be less than negative triplet. So a very popular loss function for this kind of scenario where you have some contrastive things. So you have a positive and negative, you want to contrast them. It's called max margin loss. So max margin loss is very popular. So where what you do, you create a margin. So you say, okay, my loss function will be this distance of h plus r t plus gamma minus distance of h prime plus r t prime. Okay, and I'll only consider if it is greater than 0. So what is the idea? So you want to say that even if, let's say, distance of positive sample is here, but I want to create this margin. So this is for the positive sample, it should be lower than that of negative sample, say on this distance axis. This is for the positive sample, this is for the negative sample. So this is a favorable condition, negative sample having a higher distance than positive sample, but you still want to create that margin. So even if the this difference is less than the margin, you still want to train your model, right. So that's why this plus margin minus. So if it is still positive, you want to train, but if the negative distance is here, for example, then this plus margin is already separate from the negative sample, right. So this negative sample is already above this, so then you may not want to train, right. So that's why the function that you use is, so max of gamma plus distance positive minus distance negative and 0, right. So this is another way of writing this. So if gamma plus d positive minus d negative is less than is greater than 0, then you will train, but if it is less than 0, then you are already fine. So gamma plus d positive is already greater than d negative, yes. So then you don't want to train, right. So you want, if max of them is 0, then you will not train, but if max is a positive number, then you want to train, right. So that was the idea. So you use this contrastive loss to train all these embeddings H, R and T, and you will learn the embeddings. Once you have learned, you have a scoring function to score, right. And this was just the very first method for knowledge graph embedding. Later on in literature, many other methods were proposed like TransE and so on, that used various different ideas. So you can learn more about word embeddings in chapter 6, although it may not give you many details that we had covered in this lecture. Okay. So in the last lecture for this week, we will talk about cross-lingual word repetition. Thank you.